We've been talking the last couple of days about a pendulum, and the period of a pendulum we know is related to the length of the pendulum, the string that holds the bob on the end of it that swings back and forth, and the gravitational field strength, which on the surface of the Earth we usually say is about 9.81 meters per second squared. Although, if we happen to be somewhere else or high up in a mountain, we can calculate the gravitational field strength by using stuff we learned in our last unit. The challenge with this is not so much solving for t if we're giving L or G. The challenge with this one is usually in rearranging it to solve for L or G. We've gone through this a number of times, but we'll go through it one more time. How do we rearrange to solve for L in this equation? What do you get rid of first? Michaela, what do you get rid of first here, solving for L? No, not first. Right, divided by 2 pi. So it becomes t over 2 pi equals the square root of L over G. We're getting there, but we've got a little ways to go here yet. Peyton, what do we get rid of next after we've divided by 2 pi? Good. We're going to square it, actually, right? The opposite of the square root, so it's going to be t over 2 pi squared equals L over G. Now we want to solve for L. We're almost there. Nathan, P. What are we going to do to solve for L? Good. Get rid of the G by multiplying by G. Becomes G times T over 2 pi squared equals L. Looks a little bit funny. Doesn't look as funny as when we're solving for G. Okay, let's do that now, solving for G. We're going to start off with the equation we just derived. G times T over 2 pi squared equals L. Solving for G, what do? Remember what I showed you the first day? If we had G times X is equal to L, you'd solve for G by dividing by X, right? So what are we going to do here? Good. It's going to be L divided by T over 2 pi squared. Now, in your book, you saw another version of this, which is exactly the same thing, just looks a little bit different. In your book, they squared everything inside the brackets here. They said G is equal to L over T squared over 4 pi squared, and then they multiplied by the reciprocal of this, because you guys know when you divide by a fraction, you have to multiply by the reciprocal to get the same thing. G equals L times 4 pi squared over T squared. This is a nicer formula to use, but this is a nicer formula to get to. So whatever one you like the best, go ahead and use it. Okay, this is the one that I'll use in class. Okay, but in the end, if you use this one, you'll get the exact same answer as long as you use it correctly. Got it? All right. We talked about resonance over the last couple of days as well. And we defined a term that goes along with resonance. We'll call it a prerequisite term, a term that's required to understand resonance. Okay, that term is resonant frequency. Anybody tell me what resonant frequency means? Resonant frequency is the natural frequency at which something wants to vibrate. Everything has a natural frequency, a resonant frequency at which it wants to vibrate. We knock on the desk. You hear the resonant frequency of the desk. Knock on the wall. Different frequency because there's a different natural frequency of the wall. Pluck a guitar string, completely different frequency, different natural or resonant frequency. Put your finger on the fret of a guitar, different frequency still, because you've changed the natural or resonant frequency of the guitar string when you put your finger on a fret. A pendulum, the swing set has a natural frequency, a resonant frequency at which it wants to vibrate. That's the easy one for us to see, right? Because we can literally see it. As it swings back and forth, we know the period of the pendulum is fixed. Therefore, the frequency of the pendulum would be fixed as well. If the frequency is fixed, that's a resonant or a natural frequency. We can change it by changing the length of the string. Right? The resonant frequency is now different, but it's still a natural or a resonant frequency. Then we talked about doing something with the resonant frequency. We talked about applying a force, but not just a random force. We talked about applying a force at a specific rate. Okay, not like this. Although you still see there's a vibration, right? It doesn't necessarily completely cancel the vibration. Okay, the swing set still goes back and forth, but it doesn't grow. The amplitude of the vibration doesn't get bigger. What we have to do in order to get it bigger is apply a frequency or apply a force, right, Megan, at the natural frequency, at the resonant frequency of the swing set. So we're applying it at a very specific time. That causes the disturbance to grow. That growing disturbance is called resonance. And that growing disturbance can maybe stop growing at some point, like in the swing set. At some point, there's enough energy that's dissipated from this system that it just doesn't grow any bigger. Push the swing set, eventually, it just doesn't go any higher. You got to push it really, really hard to go any higher at a certain point. But in the case of the bridge, the video that we saw yesterday that collapsed due to resonance, at least partially due to resonance, in that situation, the disturbance kept growing, and it didn't stop growing. It kept growing until the bridge broke. Okay, same as the opera singer in the glass, and so on. Got it? We assigned for you yesterday some questions on page 347. Do you have any issues on any of those questions on 347? No? Easy questions? Good. Excellent. We'll move on then. We're jumping forward now to another topic called waves. Waves, we discussed in a little demonstration we just did, are a means of transferring energy from one place to another. You jump in the swimming pool, you transfer energy to the person on the other side of the swimming pool via the wave. When you hear my voice, I'm transferring energy from me to you via the sound waves through the air. An earthquake transfers energy from one place to the other via the waves that travel through the earth. Waves transfer energy from one place to another. That's what they do. That's their nature. But what does a wave consist of? You saw in the demonstration that we just did particularly with the transverse wave, where the wave looked like this, the typical wave that we picture when we think of a wave. We saw that the particles were all vibrating like this. They were all vibrating perpendicular to the way the wave was moving. They were going back and forth, back and forth, back and forth. And when particles are going back and forth, typically we say that they're undergoing simple harmonic motion. So here's the connection. We've just jumped from simple harmonic motion to waves. Waves transfer energy from one place to the other. On the surface, they're completely different than simple harmonic motion. But the nature of the waves comes from the simple harmonic motion of individual particles. That's why we're doing both of those in the same unit, simple harmonic motion waves. Because really, although we're looking at it from a different angle, we're still doing simple harmonic motion. Now, there's two types of waves that we talked about. There's other smaller types as well, but we'll focus on these two. The first one is called the transverse wave. And a transverse wave is that wave that we typically think of when we think of a wave. You're standing by the side of the ocean and you see water waves coming in. Okay, that's what you think of as a wave that has a high point and a low point and a high point and a low point and so on. That's a transverse wave. Versus a longitudinal wave, which we don't picture this so much as a wave because we usually don't even see longitudinal waves, but they do exist. They happen in earthquakes. They happen in sound waves. Sound waves are longitudinal. They're waves that look more like this, where we have areas of high density, or the particles that are making up the wave are close together. And then we have areas that are low density. So the particles that are making up the wave are further apart than high density, then low density, then high density, and then low density, and so on. The particles in that wave are vibrating parallel to the way the wave is moving, right? Perpendicular, parallel to the way the wave is moving. But in both cases, it's simple harmonic motion of those individual particles. Now let's label a few things here. Let's label a term called wavelength. 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 What do you think wavelength is? I'm going to give you a bigger diagram here so we can see it a little bit better. The wavelength is literally the length of a wave. It's the distance over which the wave repeats itself. Now, it's given by a symbol, Greek letter, lambda, L-A-M-B-D-A. It's like an upside down lowercase y, lambda. It is the wavelength. It is the distance over which the wave repeats itself. We can label that in a number of spots. There's one spot that's already labeled up there from crest to crest. That works just fine because the wave starts here, it repeats itself here. We could also label the wavelength here from trough to trough, repeats itself over that distance. We could also label it here. The wave repeats itself over that distance. We could also label it here for that matter. The wave repeats itself over that distance. The wavelength measured in meters, given by the symbol lambda, the distance over which the wave repeats itself. A crest, we'll call a symbol C, although that's just a made-up symbol. It's going to be here or here, anywhere that's at the top of a wave. I grew up in Nova Scotia and learned to drive in Nova Scotia. I don't think you see these signs anywhere in Alberta. I don't think I've ever seen them, but when I was growing up in Nova Scotia and learning to drive in Nova Scotia, one of the signs that was in the driver's manual, and one of the signs that you would often see as you come up over a hill, would be a sign that would say, blind crest. That would mean that as you were driving up over the hill, going to go down the other side, that would be quite the hill. They usually weren't quite like that, quite that sharp in Nova Scotia, because if you're going too fast, you just go way over here. Usually weren't quite that sharp, but you get the picture. You go up over the top of this hill, what it means is that you couldn't see over the crest of the hill. Right? It was a blind crest. In other words, maybe if somebody was passing coming up the other way, be careful, because you can't see when you're over the lip of the hill, over the crest of the hill. Maybe somebody was going to come out of a driveway, and you couldn't see them coming out of the driveway. So just be careful, because you can't see over the crest of the hill. A crest is the top of the hill, or the top of the wave, okay, the lip of the wave, the high point of the wave. A trough, on the other hand, think of like a feeding trough, like a pig trough where pigs eat from. It's like a dip, right? Okay, looking at it from the side, this might be a feeding trough. The pig dips its head in there and eats all the food from the trough. This is going to be a trough right here, the low point of the wave. Maybe another one over here, and so on. Everywhere you have a dip in the wave would be a trough. And finally, the amplitude of the wave, which is really just the size of the wave, which is related to the energy. Remember, waves carry energy, that's what they do. The amplitude of the wave is related to the energy of that wave. Okay, the bigger the wave, the more the energy the wave is carrying. If I drop a little rock into the water, it generates a wave, because the wave carries energy from that rock. If I drop a brick into the water, if I drop a car into the water, then we're going to produce a bigger wave, because a higher amplitude wave, because that wave is carrying more energy. The amplitude is the size of the wave measured from the equilibrium position. So it would be to the top of a crest from the equilibrium, that's the middle of the wave, or it would be to the bottom of a trough from the equilibrium position, or from the middle of the wave. This is not the amplitude. Okay, that's wrong. That's twice the amplitude. It's arbitrary, but in the end, we always measure it from the equilibrium position. And remember, amplitude is related to the energy. It was 2005, I believe it was. Boxing Day, I think, 2005, there was a massive earthquake off the coast of Indonesia, in the Indian Ocean. Do you guys remember that? You might not remember the earthquake, but you guys remember hearing about that? There was a massive tsunami that was produced, and it wiped out, it killed something like 150 to 200,000 people. Like we're talking about 1/5 of a million people that were wiped out by a tsunami. How is this tsunami produced? How is this big, powerful wave produced? Well, waves carry energy, right? And the amplitude of the wave, the size of the wave, is related to the energy that it carries. If you've got a big earthquake in the ocean, where does the energy go? Got to go somewhere, right? It gets transferred somewhere by waves, by water waves. So those water waves become big because they're carrying energy from this massive magnitude 8 earthquake to the earth, to the ground, or to the shore, I should say. What about the other kind of wave? Not a very good diagram here, but you can still see that there's areas of higher density right here, and then areas of lower density beside it. We call the areas of high density compressions, because that's where the particles are compressed. Notice the particles are going back and forth in the direction of the wave motion, parallel at least to the direction of the wave motion. Compression, refraction, where the waves are a little bit more spread out, and then a compression, and so on. So we're going to say a compression is an area of high density in a wave. And a rarefaction, not refraction, rarefaction is an area of low density in a wave. Let's go just a little bit further, and then we'll leave it after this. We talk about the energy of a wave being related to the amplitude, the size of the wave. We talk about the length of the wave, the size of the wave, or how long it is, I should say. We talk about which way the particles move. But remember, it's not only the particles that are moving in their own little localized area within the wave is moving as well. Now, the particles in Indonesia, when there's a massive earthquake in the Indian Ocean, the particles of that water aren't being transferred to Nova Scotia. The wave can go that far, but the particles within the wave aren't traveling that far. The particles in the wave are traveling in their own little area, but the wave itself can travel that far. In some cases, it can travel pretty quickly. The wave speed is how fast not the particles are moving within the wave, but rather how fast the wave itself are traveling. And the basic equation that describes wave speed is V equals d over t. As long as the medium doesn't change, as long as the material the wave is traveling in doesn't change, then the speed isn't going to change. If you have light waves traveling in air, and then those light waves go into glass, then the speed changes. But if the light waves stay in air, then it's not going to change. If you have water waves traveling in the ocean, they're going at a certain speed unless they reach a different part of the ocean, which with a dramatically different depth, then the speed's going to stay roughly the same. By the way, if water waves do encounter a different depth, they do change speeds, and that's why when water waves come into the shore, that's ultimately why they end up breaking. Okay? That's why they crash into the shore, is because of a change in speed when they're going to the shallow water. We'll assume that they travel at a constant speed, though, and that speed is v equals d over t. Now, the distance over which the wave repeats itself is the wavelength. The time over which the wave repeats itself, hey, we didn't talk about this. The time over which the wave repeats itself. What do you think I'm going to say that is? No, close though. What is it? The period. Right? The period is the time over which the wave repeats itself. Right? We're talking about simple harmonic motion here. It's just kind of an application of simple harmonic motion. Period is the time over which anything repeats itself. You could say V is equal to lambda over T. But Nathan, you said frequency, right? We are going to tie it into that. The period is equal to 1 over frequency. So therefore, we could say, if we wanted to, V is equal to lambda over 1 over F. Now, that looks a little bit ugly. So instead of dividing by 1 over F, we'll multiply by F over 1. The equation that we want to get to here, we call it the universal wave equation. It says V, the speed of the wave, is equal to the frequency of the wave times the wavelength of the wave. Now I'm going to circle something here. Frequency, measured in hertz. This is the one. This is the variable that stays the same. Once a wave has been made, the frequency doesn't change. The speed can if you go to a different material. The wavelength can if the speed changes, but the frequency won't change. Once it's been made, it stays the same. Let's take a look at an example here. 409, example 8.2 says, to generate waves in a stretched spring, you oscillate your hand. What does oscillate mean again? Simple harmonic motion, back and forth. You oscillate your hand back and forth at a frequency of 2 hertz. If the speed of the waves in the spring is 5.4 meters per second, what's the wavelength? It's a pretty straightforward question, I think, right? We got the frequency of the wave, and the frequency of the wave never changes. So even if that wave is to go into a new material and change speed and change wavelength, the frequency of the wave is dependent only upon what caused it, and that's your hand vibrating back and forth at 2 cycles per second. That's not going to change, the frequency, unless you change the way your hand is moving. The speed of the wave is 5.40 meters per second, and we're looking for the wavelength. We've got 2 equations that we're allowed to use for speed of wave. V equals d over t, and we've got V is equal to F times lambda. Probably going to use this one here, right? Rearrange it, though, to solve for lambda. It becomes V over F. 5.4 meters per second, divided by 2.00 hertz. Do the math. 2.70 units meters. A number of years ago, Friday, we're going on a field trip to the amusement park, right? A number of years ago, there was a group of, I think, 5 students who, as part of a special project they were doing, decided they needed to take some measurements at the water park as opposed to the amusement park. So instead of going to the amusement park, me and 5 students went to the water park, when Mr. Coder and the rest of the students went to the amusement park. When we went to the water park, they took a number of measurements, including heights of rides, so they could find energies and all kinds of things. But one of the things they did is looked at the wave pool. When they looked at the wave pool, their goal was to find the speed of the wave. So how do they find the speed of the wave? They measured the wavelength. How do they measure the wavelength? Well, the distance between one crest and another crest, right? It's pretty easy to find. Okay. How do they find the frequency? Anybody want to take a stab at that? How do they find the frequency of the wave? They stood in one place and they counted how many times the wave went up and down per second. So over a period of 10 seconds, 20 seconds, I don't remember what it was, what they did, they counted how many times the wave went up and down, and they found the frequency. And then from that, it's just a simple calculation, right, to find the speed. V is equal to the frequency that they found times the wavelength, and we got the speed. Okay. All right, 3 questions to go along with that on page 409. Let's give those a try, please.